Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 32. In the last module we were talking about how to design and place a riser, and in context of that we had started doing a numerical problem where we wanted to determine the dimensions of a cylindrical riser to be used for casting as aluminum cube of sides 15 centimeter. The volume shrinkage of the aluminum during solidification was assumed to be 6.5%, and then we step by step try to figure out how to get the optimum V by A condition corresponding to the solidification of the riser, time of solidification of the riser being greater than the time of solidification of the actual melt which is in the cast itself or the molding cavity itself. So, in that context we did a few things which I would like to just repeat for the sake of recall before we go ahead into the finalization of the design. So, first of all, let us determine the diameter to height ratio, and this is what we did in the last module as well, of the most compact cylinder, so that for a given volume the surface area is a minimum. So, if we assume let us say D and H to be the diameter and height of the cylinder respectively, then we found out that the total area of surface of the cylinder would be equal to pi dH plus twice pi by 4 d square. Obviously, a cylinder has a curved surface as well as two flat surfaces on the top and bottom. Okay, so, this is the curved surface area, this is the top surface area, pi by 4 d square and two such surfaces together. So, that is the area. Similarly, the volume of the cylinder was obtained as pi by 4 d square H, and we made a formulation from which we found out what is H in terms of volume. So, it was 4 V by pi d square, and we substituted that back into the area equation here. So, that we were left with pi d times of the value of H, which is 4 V by pi d square plus twice pi by 4 d square. So, that is how we obtained the final area, and this was 4 V by d plus pi by 2 d square. If you may further recall, we tried to minimize the area with respect to the varying diameter, meaning thereby that the whole goal here is that the volume the A by V ratio for the cast vis-a-vis the A by V ratio for the riser needs to be calculated. So, here for example, in this particular case, because it is a cylindrical riser, we are just trying to calibrate what is the A by V ratio corresponding to the optimum heat transfer condition. So, finally, the time of solidification of the riser should be greater in value than the time of solidification of the cast. That was the final condition that we wanted to sort of apply in this particular case. Okay. So, So, we minimize the area here, and for that we used the derivative of A with respect to d and equated that to 0, and we obtained a condition which was 4 v by d square plus pi d equal to 0, or d cube equal to 4 v by pi. So, that was what the condition was in this particular case, and we already know that 4 v by pi was actually equal to h d square. So, therefore, d equal to h was considered to be the optimum condition for minimization of A with respect to d. So, with that we calculated the minimum volume necessary for the riser, which is actually 6.5 times the volume of the cast, but 3 times of that, just because 3 is a factor of safety as I had discussed earlier. So, V c is the cast volume. In this particular case, V c is nothing but 15 cube centimeter cube, that is 3375 centimeter cube. The premise is that you want to cast an aluminum cube of side 15 centimeter. So, with this kind of V c, we could obtain the volume of the riser here to be equal to 658.2 centimeter cube. Further, we obtained the d equal to h as 4 V r by pi to the power of 1/3, and that was corresponding to 9.43 centimeters, which is equal to the diameter of the height of the particular cylindrical riser, and then we calculated A by V for the riser, which is 6 by d or 6 by h, whatever you may call. In this particular case, it is 6 by 9.43 centimeter inverse, which is 0.636 centimeter inverse. Similarly, we calculated that of the cast is A by V cast equal to the 6a square surface area divided by the volume of the particular cube centimeter inverse. This came out to be 0.4 centimeter inverse. So, the riser was found to have smaller solidification time and it would not simply meet the condition that area by volume for the riser is less than or equal to area by volume for the solidification time, okay, of the cast. So, we have to do a force fit, and we try to do that by forcing the volume by area ratio to behave in this relationship, so that the time of solidification of the riser, which is actually proportional to the volume by area of the riser. Okay. So, in that case, the time of solidification should be of the riser should be more than the time of solidification of the casting. Okay. So, when we force fit this condition, we already have formulated the area by volume for the riser as 6 by d or 6 by h, which was actually calculated earlier, but now we have to consider the new dimensions d and h, which would satisfy then the condition A by V of the riser less than equal to A by V of the casting. So, the A by V of the casting has earlier been calculated to be 0.4, and so we simply have the force fitted condition as 6 by d is greater than or equal to 0.4 or less than or equal to 0.4 centimeter inverse, In other words, d is greater than or equal to 15 centimeters. So, this would be the value for the d for which corresponding to which the area by volume of the cast would at least be equal to that of the area by volume of the riser. So, condition would be obeyed in one sense, that at least both of them have equal solidification times. And now, let us actually see that with this kind of diameter, what is going to be the kind of volume that we need, or is it going to be again sufficing to the 6.5% requirement that we have. So, with minimum value of d, the volume of the riser simply now becomes pi by 4 d square h, or in this particular case pi by 4 d cube, which is 2650 centimeter cube. Now, this volume is much more than the minimum volume of the riser that is necessary, and in that case you have already seen that that volume is actually equal to 6.5% and 3 times of that is amounting to about 658.2 centimeter cube. So, obviously, this value of 2650 centimeter cube is much higher in comparison to the volume that is necessary. So, on one hand, with the diameter equivalent to height optimum condition, we are getting a riser volume which is much above the requirement. So, we are wasting metal this way, and that is something that we should not be allowed to do. So, we consider the top riser and see what happens in that particular case. Okay. So, let us now consider the top riser. That means, you have the cube right about here, and on the top of it you have the cylindrical riser sitting on the top of this particular cube. This is the riser, this is the cavity. Okay. So, now what effectively would happen is that the area of the cylinder or area of the riser becomes a little different. The area now becomes equal to only pi by 4 d square plus pi d h. Okay. That is the curved surface area as well as one of these areas, the other area being same as the area of the top of the cast. So, it is a common face, you can say, and so we do not consider that as the area anymore through which heat transfer would take place. Okay. So, in that event, now if I do the dA by dd, so we get twice pi d plus now we have to substitute for h here, and h was substituted earlier as 4 v by pi d square, and effectively this turned out to be 4 v by d. So, in this particular case, this comes out to be twice pi d plus minus 4 v by d square. Okay. And that is equated to 0 for the optimum condition. So, in this particular case, the optimum condition becomes equal to twice pi d equals 4 v by square of d, and the way that we can think of this is that the d cube becomes equal to 4 v by twice pi, and 4 v by pi is already known to be d square h. So, it is d square h by 2, and therefore, the optimum condition here becomes equal to d equal to h by 2. Okay. So, just because of this area being removed, because it is no longer a heat transfer phase, the optimum condition changes from d equal to h as earlier to d equal to h by 2 as in this present case. So, in this particular context, if we wanted to sort of calculate again the area by volume of the riser. So, the area by volume of the riser still remains same 6 by d, okay, and the volume the relationship that we have for the optimum area is d equal to h by 2. So, with a large top riser, the cube loses its top surface for the purpose of heat dissipation, and hence if I now calculate what is the area by volume of the cast, this becomes equal to again instead of the 6 faces that we had earlier, this face now no longer is a heat transfer face, okay, because there is liquid metal on the top of it, and so the other faces are all responsible for all the heat transfer, although there is going to be some heat transfer depending on if the temperature of the metal is little different here, but we consider that to be very negligible, because again the temperature of the metal in the riser as well as in the cast before the solidification has happened is more or less in the same temperature zone, unless heat transfer takes place from the other phases, etc. Okay. So, here for example, then the area by volume of the casting would become 1/3 centimeter inverse, and we therefore now have the 6 by d area by volume of the riser to be less than or equal to this 1/3 centimeter inverse, or diameter greater than or equal to 18 centimeter. So, the riser volume with minimum diameter now is given as pi by 4 d square h. In this particular case, it would be pi by 4 times of square of 18 times of h, which is 18 by 2 because of the optimum condition which has been hit upon here. So, that becomes equal to 2289 centimeter cube, which is very close and reasonable to the value that had been earlier obtained as 2650 centimeter cube, the minimum riser volume that is necessary. So, we are saving a lot of metal here if we do this second iteration where we assume this top risering with a common face, and if you slightly change the design of the riser, now you can see that just by eliminating one interfacial area from the cast as well as the riser, you are left with a situation where with the minimum amount of volume you can still make it to be sufficient to accommodate for the shrinkage volume of the casting, and you can also do the risering. So, that is how you have to design the riser geometry as well as the placement of the riser with respect to the cast surface. So, to check the adequacy of the riser for a steel casting, normally people use this Keynes relationship. So, we have found out earlier that the solidification time is proportional to the square of the ratio of volume to surface area. So, the Keynes relationship is based on the assumption that the cooling rate is linearly proportional to the ratio of the surface area to volume, and based on this they draw this typical risering curve which is depicted here. So, this is the volume ratio of the riser to the cast, and this is the freezing ratio of the area by volume of the cast with respect to the area by volume of the riser. And what you can see here is that anything on the right of this particular line drawn, separating the sound from the defective castings are all sound castings, and to the left whenever the freezing ratio falls down beyond this particular line, okay, for a certain volume ratio it becomes a defective casting. So, the ordinate of a point on the curve shows the volume ratio and the abscissa, the freezing ratio. Also, the subscripts C and R are referring to casting and risers, as I think you have mostly understood from all my notations done earlier. And for a given casting riser combination, if the point on this figure falls to the right of the curve, the adequacy of the riser is ensured. So, we want to design for all those freezing ratios which are towards the higher side here, right about in this particular region, okay, and avoid all the freezing ratios where the casting may be rendered defective. And the equation of the risering curve is of the form x equal to a by y minus b plus c, where a is the freezing constant for the metal, b is equal to the contraction ratio from liquid to solid, and c is a constant depending on the different media around the riser and the casting. So, with this I would like to end the module on design of riser and placement, and this also completes incidentally the section on castings. The next section in the next module that we will take up is the metal to metal conventional machining processes. For now, I would like to bid goodbye. Thank you.